Okay, problem number 24 in section 4.6 is asking us to put together everything we've learned right here and come up with a whole bunch of stuff. As I'm reading the directions in front of me here, they want us to find the transition points, meaning a maxima or minimum, intervals of increasing and decreasing, concavity, asymptotic behavior, and we're supposed to come up with a sketch of the graph. So this is the function that we're dealing with, x squared times x minus 4 quantity squared. And I have to tell you guys, that since we're looking for spots of increasing and decreasing and concave up and concave down, all that work is going to require both the first and the second derivative. I think it would be a really good idea then, and I don't think it would be too difficult in this problem, to take this function right here and expand this polynomial. I think that's going to make it much easier to come up with first and second derivatives. So because this one isn't that bad, I'm going to leave the x squared there, and the x minus 4 quantity squared is going to give us an x squared minus 8x plus 16, and then I'll go ahead and distribute the x squared now and get an x to the fourth minus an 8x cubed and a plus 16x squared. I think that's going to make life much, much easier as we go through this problem. Now, knowing where we're going with this, I'm going to go ahead and draw a line right down the middle of my page here, and I'm going to deal with our first derivative right here. Even though this was y, I'm going to treat it as an f of x. I just kind of like that notation better, and here we go. First derivative then, f prime of x, is going to be a 4x cubed minus a 24x squared plus, that's going to be a 32x there. We're going to set that equal to 0 and try to solve that. So let's see how this is going to be. I'm going to factor out a 4x. That's going to leave us with an x squared minus a 6x and then a plus 8 is equal to 0. And my hope was that that was going to factor, and I think it is. We're going to get an x and an x here. Signs are going to be the same in both negatives, so minus, minus, and it looks like we're going to have a 2 and a 4 right there. Yep, and that'll give us what we need. So from the first derivative, we're going to get critical points now at x equals 0, another one at x equals 2, and a third one at x equals 4. Notice, guys, there is no limited domain on this function, so we're going to assume it's the domain of the whole function, and since it's a polynomial, that domain is all real numbers. So all three of these critical points are in play, so I'm going to go ahead now and make, let's see, with 3 critical points, we're going to make a 4 interval sign chart here, and we're going to come up with some test values all around there. So how about x equals negative 1, x equals positive 1, let's do x equals 3, and we'll go with x equals 5. And the best place to put these points, guys, since we want information about behavior right now, it's got to go into the first derivative, but we could either put that here or here or here. It's definitely the fully factored version of the derivative. That's the easiest place to go with that. When I put in a negative 1, this factor right here is going to become negative. This one will be negative, and so will the third. Negative times negative times negative. Our first derivative there is negative. So I'll say f prime is less than 0, and that means that f is going to be decreasing on this interval. Let's move on now to x equals 1, where we're going to get a positive and then a negative and a negative. So f prime there will be positive, and f is increasing on this interval. Now, when x is 3, we're going to have a positive, positive, negative. So f prime will be negative again, and f is decreasing once more. And then when we let x equal 5, positive, positive, positive. So here f prime is greater than 0, and f is increasing yet again. So if I look at what I wrote there on the bottom of that column there, guys, with everything about f, we can see that at x equals 0 right here, we have a minimum value. Okay, so a minimum at x equals 0. I don't yet know if that's an absolute or a relative min, but that's what we can say right now. And we've got another minimum right here at 4, where our derivative changed from negative to positive. So one minimum at x equals 0 and another at x equals 4. And then right here at x equals 2, our function was increasing, then decreasing. So we know that we have a maximum here at x equals 2. Now, knowing what I know about a positive fourth degree function, this thing has end behavior that takes it up towards infinity on both sides. I do know for a fact right now that this maximum we have right here is a relative max. at x equals 2. When it comes to those two minima that I got at 0 and 4, my guess is one of them is an absolute minimum and one of them is a relative minimum, but I don't know that for certain just yet. Okay, that's as far as I'm going to go right now with coming up with the value of the first derivative. And let's move on to our second derivative now, guys, where, let me switch colors here just to keep things separate, where f double prime of x, I'll just take the derivative of f of x right here. Looks like it is going to be a 12x squared minus a 48x plus 32. That's going to equal 0 as well. So what can we do there, guys? Looks like we can factor out a 4, and that's about it, from, let's see, a 3x squared minus a 16x plus 8. All of that is equal to 0, and now I'm curious as to whether or not this one is going to factor any further or not. Let me try to play with this real quick. We'd have a 3x and an x. Signs are the same and both negative, so minus minus. And let's see, two numbers that multiply to 8, and we need to get them to equal 16 after we multiply one of them by 3. Let me think here. A 4 and a 2. No, a 2 and a 4. I don't think that's going to work. How about an 8 and a 1? No and no. I'm pretty sure, guys, that this one right here does not factor. We'll find out in a minute if I'm right or not. So I'm going to go to my calculator and ask it to solve this quadratic equation right here. If it comes up with rational solutions, I'll know that I was wrong and that it did factor. But if we get something ugly and irrational, then we'll know that I was right. So let's see. Let's see here. Calculator should be here somewhere. And let's go to menu, and then it's 31 for you guys to solve. And our equation, I believe, was a 3x squared. And then what? Actually, excuse me, a 12x squared minus 48x plus 32. Boop. Okay, let's try that again. Okay, so a 12x squared minus 48x, and then a plus 32. All of that was equal to 0. We'll put a comma there and ask it to solve for x. And when I hit enter, yeah, we got these ugly decimal numbers right here. Boy, it didn't even give it to us in radical form. That's interesting. So that tells me that I was right. That quadratic did not factor. I'm assuming I typed it in right. Let me check that one more time. 12x squared minus 48x plus 32. Okay, got it. So we're going to write those down to 3 decimal places. 0.845 for the first one. Okay, gotcha. Or x equals, and then what was here? 3.155. Okay, this doesn't shock me, by the way, guys. When you're writing a problem like this, it is very difficult to get a polynomial whose first derivative has rational solutions and then to get its second derivative to do the same. When I've tried to make problems that do that, it's pretty difficult to come up with there. Okay, so we now have 2 values here from the second derivative where it was equal to 0. So these we would call potential points of inflection. So let's pick some test values, guys. Something less than 0.845, we'll go with 0. In between the two, we'll go with 1. And greater than 3.155, we're going to go with 4. And we will put those into the second derivative. But boy, this is going to be ugly because those are nasty numbers to deal with right there. I think what I'm going to do is I'm going to go ahead and define a function in my calculator here. So actions define, and let's call this, where's my f hiding? There it is. So we'll call this, we'll just call it f of x. Let's go with that, okay? Is equal to, and here's that second derivative that we came up with, 12x squared minus 48x and a plus 32, and that should do that. And now we want to evaluate that f function at our first test value, which I thought was 0. Oh, actually, that one I think I can do without the calculator. When we let 0 go into this function right here, looks like we're going to get 32. So f double prime is positive there. Our curve is concave up. When we get to x equals 1, that one I can probably do without a calculator too. That's 12 minus 48. That's a negative 36. Adding 32, we're negative there. So f double prime is less than 0. We're concave down. on that interval here. And I have a feeling when we plug in 4, we're going to get something positive. But let's just see, since I did all that work there. Yeah, f of 4 then ends up being positive. So f double prime is greater than 0, and we are concave up. So it looks like the second derivative changed sign at both of those x values right there. So we have a point of inflection at x equals 0.845 or at x equals 3.155. 2 points of inflection for that one. Okay, what else is going on here, guys? Oh, they wanted intervals of increasing and decreasing. I think we have that information right here. This first interval is an interval of decrease from -infinity to 0, then increase, and so on and so forth. And then we've got intervals of concavity here as well. We're concave up from 0 to 0.845, again on the right from 3.155 to infinity, and we're concave down here in the middle. The other thing that I think we're probably going to need to do right now, and I'm going to switch to green for this, is we need to go ahead and, since we're supposed to graph this function, we have to come up with the actual y values of all of these points that we came up with. So a couple of these aren't going to be all that bad. Like, for example, when x is equal to 0, I'm just going to cram an ordered pair in there. We plug a 0 into this function, and this first factor right here is going to end up equaling 0. Well, then we don't care what the second factor is. 0 times anything is 0. So we've got a minimum there. We have another minimum when x is equal to 4. Well, in this case, if we put a 4 in right here, 4 minus 4 is 0. That whole thing is going to be 0 as well. But when we plug a 2 in there, this might be a little bit harder to do, but I think we can probably do it by hand, guys. 2 squared is going to get us a 4 there. 2 minus 4 is -2. Squared is going to be 4. That's going to get us the point 216 for our relative max. Now, unfortunately, these next two are decimals, which means they're going to come out really, really ugly. So I do think I'm going to need the calculator for this. And now what I think I should probably do is define the original function here. So let me go to menu 1.1, and I'll call this one f1. Probably how, you'll see why in a second. f1 of x, and that is going to equal, the original function right here was x squared, and that gets multiplied by, in parentheses, that was an x, was it x minus 4 quantity squared? That's what I forgot. So x minus 4, close it, square it, so there's our original function. And now we're going to need the calculator to evaluate for us f1 at this first point of inflection, 0.845. Gotcha? 7.107 is what we get right there. Okay, and then again at 3.155. So let's try that. So f1 at 3.155, and we get, oh, that's interesting, the exact same value again there, 7.107. Wasn't expecting that to happen, but okay. And that's where we're at. So now, boy, there's a lot going on this page right here, guys. We're going to scroll this thing down a little bit, and I think that everything we need, I think I can see right there. Okay, so let's come up with a graph. This certainly doesn't need to be super accurate, you guys, but x-axis and a y-axis. And as I look at all the x values that I need, kind of looks like everything is between 0 and 4. I really didn't need much to the left of this graph at all. So I'm going to try to use my space and go 1, 2, 3, 4 units out to the right. I'm going to go one more actually and go to 5. Okay? And then from there, if we take a look at the y values, now this gets a little bit interesting. All of them are positive. So I think that means I probably could have moved everything down here, maybe like that. I lost my 5 right there, okay? And maybe I should have gone a little bit higher on my y-axis. Looks like the maximum y value that I have here is 16. So I'm just going to put that 16 anywhere I want and then scale it from there. Halfway there would be an 8, here would be a 4, here would be a 12, and that's probably good enough. All right, guys, just kind of reading this information now from left to right, we've got a minimum right here at 0, 0. Okay, another minimum at 4, 0 right there, a maximum in between at 2, 16. So that's roughly right about there. A point of inflection at 0.845. That's just a little bit less than 1, and a y value of about 7. None of this needs to be perfect, you guys. And another point of inflection at just over 3, and then that same y value again. And now if we kind of read this, we see that the function has to decrease and be concave up before it hits that first point. So it would probably look something like this. Then, after that point, we are now going to be increasing, but still concave upward until we get to this point right there. After that point of inflection, which occurred right here at 0.845, now our function is concave downward, but it's still increasing to that point. That's a maximum, so now we go from increasing to decreasing, but still concave downward. But now we just hit our second point of inflection, so now we're going to be concave up, but still decreasing, so that's going to look something like this. And then the last interval here and here, the function is going to increase and be concave up, kind of looking like that. So boy, that is a messy graph there, but that kind of does just about everything that I needed it to do here on this page. So maybe I can move. Oh, that was a horrible idea. Let's not do that. Okay, anyway, that's about what our graph is going to look like. So a lot of work right there involved on problem number 24, but that's what the final result should look like.